Hi everyone, my name is Jesse Butler. I am a senior developer advocate in the AWS Container Services team, and I'm going to talk with you about building resilient Kubernetes deployments with AWS App Mesh. I'm taking some liberties on what a 300 level talk is. I think in this space there are so many options. Just the other day on Twitter I saw a thread on building pipelines in Kubernetes, and of a dozen replies, they were all valid. So this is not going to be a sort of cut and paste, do this and you have a solution type of talk. But I am going to share some opinions and some sort of use cases around using App Mesh, Service Mesh, to build resilient Kubernetes deployments. So there's a lot to cover, so let's dig right in. Just to go through a quick agenda, we do have to set some context, so sorry about that. Most of your sessions are going to start with some number of minutes of things that you might already be familiar with, but I think it's really important that we set some context around why we're looking at building things the way we are and why we'd even consider using AppMesh as part of that solution. So we'll talk about modern application deployments, and we'll talk about deployment options with Kubernetes, and then we'll talk about leveraging abstractions and automation. So just to set some context here up front, simple applications can benefit from simple solutions. So a lot of things work fine on a small scale. What we're talking about is when we plan for scale and things become a lot more complex. We have a lot more moving parts. We're looking to microservices architectures where we have any number of services, dozens or hundreds of services, each one being deployed as hundreds or thousands or tens of thousands of containers. That's a lot of ephemeral moving parts. And when we're designing for scale, in AWS, we like to think in terms of benefits to the customer. And for me, I think I relate those to sort of design concepts in applications. Agility, sanity, and resilience are concepts that I like to think about when I'm considering applications at scale. And I will say that resilience I use intentionally. A lot of people say, "Do you mean reliability?" I think of resilience, the ability of a system to sustain failures and to manage changes over time as an important factor. And I think reliability comes as an aspect of resilience. So what we end up looking at is really sort of table stakes for building cloud native applications. So we want to separate our concerns. We're looking at 12-factor applications. We're thinking about using microservices architectures, and we're building things at scale as these loosely coupled, discrete components that work together. And functionally, we're keeping, those aspects to those components. And so that allows us to do more effective iteration. When we're starting to look at, building features or testing lines of code, changes in, say, 1,000 lines of code versus 1.5 million lines of code, we can effectively iterate a lot better. And when we're designing these components to use RESTful APIs and to work together sort of this in these really transparent ways, we can maintain better quality over integrations. And these deployments are actually, you're able to do a lot more and be a lot more aggressive and pushing out new features more frequently. And I think it's important to note that containers are really a huge part of, at least in the implementation, a lot of this methodology coming into play. And Docker has a lot of, should have a lot of credit in that. At least for Linux container development, it really changed the way that we build and run software at scale. But obviously, when you're using, something like a Docker run on your laptop, and then you bring it to test, and then you bring it into production, many instances of containers, you don't really want that working off of just a bunch of Docker runs because they're ephemeral, and you don't really have any way of monitoring or finding out where problems, may have occurred. And that's where container orchestration comes in. And with AWS, you have two clear options for managed container orchestration, ECS and EKS. These are both fully managed container orchestration services, and we see customers selecting between these on a number of criteria, whether it's sort of the team culture or the flexibility of the solution, personal preference, really. For this talk, we're talking about Kubernetes, so I'm going to refer to EKS. So Amazon EKS is upstream Kubernetes with a lot of the hard parts handled for you by us. And what I mean by that is sort of the undifferentiated heavy lifting of creating clusters and managing their life cycles. It's handled for you with our fully managed control plane. And we also have a lot of data plane automation with managed node groups, and you can even choose to adopt serverless containers with Fargate. So now we've decided that, yes, we're going to use microservices architecture for applications. We're going to use containers. We're going to use Kubernetes. So where does that bring us? And that brings us to the same place we've always been when building and shipping software. It's lifecycle management. At the end of the day, you're writing, building, shipping, running, breaking, and sort of iterating over this process with code. That's really what we're talking about when we talk about lifecycle management. Whether you're fixing a bug or putting a new feature out, that's this cycle that you go through. You're developing, building, testing, deploying, and monitoring your code. And when we look at code, it's really changed over the years, especially in recent years, to include a lot more than just the source code explicitly for your services. Yes, that's very important, but you also have the Docker files, which define how the code is built, and your Kubernetes manifests, which define how that is run. We also have infrastructure as code, so you have CDK and CloudFormation and Terraform. All of that is code. Really, it's sort of, you see a lot of threads on Twitter that are, oh, YAML isn't code. It doesn't matter. Really, any text in a file that is going to dictate how your application behaves, you should look at it as code. And you should also have a goal of owning less code. There's a lot of stuff that can be done with software. That's either your software that's customer facing or software that exists to run your software. And what you really want to do is try and move beyond owning more code than you need to. And so you end up with a lot of code, even in that where even beyond automation, just sort of the service code, Docker files, Kubernetes, and source control or revision control becomes really important. This is the way for you to tell the truth in your application and your infrastructure. At any given point in time, you can look at git commit and say, okay, this is the state of the code. I can build the code. I can run it. I know what's happening. The correlation between that code state and the sort of the running bits that you have is very vital to being able to maintain your code and monitor it and know what you're trying to triage and fix issues with. And so we look to container images as an immutable artifact of the state of your code at a particular point in time, which is why I tend towards saying that latest isn't really the greatest container image tag. However, I'm not going to say don't use it, but I will say it's very vital that you can correlate the sort of the state of your code to the running bits. So meaningful tags are meaningful, right? You can use a commit ID, you can use semantic versioning, you can use vanity names, of course. You can use prod and release or staging, but just make sure that your teams can easily determine what the actual code is that's running. So looking at using a meaningful tag, this is what I mean. We're developing code, we do a git commit, it has an ID. We can build a container image which uses that ID as its tag, and we know at any point when we're looking at that image that that's the code that's running there. We can put that into test, we can push it through our pipelines out into deployment, and at any point in time as we're monitoring that code, we can see exactly what's happening. We know exactly what's going on in that particular instance because we can look at the code. So we can correlate these two things. So now that just brings us to a place of how do we actually work through that cycle of an update? And native Kubernetes has a strategy for rolling updates that works really quite well, especially if you know how to use them and you do a little planning. And depending on what your needs are, this could be all that you need. However, as we had said, things get big. There's a lot of moving parts when you scale up. Looking to plan, it has some limitations. So let's talk a little bit about how they work. So the rolling update effectively will cycle pods out. Old pods are killed off, new ones are spun up. And the containers that are running within them will get sig terms, and those processes will be killed off. And then the new pods will come up. And as soon as those new container processes are running, Kubernetes considers them ready, and we'll start, work will start coming at them. And they might not actually be ready for that. You also have a lot of ordering, so if your pod has 3 or 4 containers in it, there's no order to how they're killed off and started up. And then there are, service configurations in the cluster may lag a little bit. So there are a lot of things that you need to take into consideration. They're typically handled in Kubernetes itself. There's a lot of features to help with this. For example, implementing liveness and readiness probes. Startup probes are really great. That's new in 116, which gives you a blocking call out to you make sure that the pods that are starting up are actually ready. And there's a little bit of a ballet dance here. There's really good documentation in the upstream Kubernetes docs on this. Obviously, make sure that your services, the code that you're writing, can handle a SIG term. Specifying pre-stop lifecycle hooks is really important. This gives you a synchronous call while the pods are being killed that will execute, and it's blocking as well. So this gives you an opportunity to clean up and close down sessions, stuff like that. Regardless of however you handle this, you need to just plan for the upstream and downstream interruptions. So I like to just suggest that even with long-running, very mature services, which might deploy and stay running for months or even years at a time, that's not a great idea. And I like to suggest that you actually do some some cycling on a regular cadence. This gives you the ability to know that you can swap these services in and out, and they're ready for an update. So even with all of that in place, it only gets you so far. And in modern infrastructure, you have a lot of options for being really creative about how you build your deployments. And with rolling updates, you really only have the ability to move from one version to another. You can really only start, pause, and roll it back. And there are some limitations with it. And they can work really well. But planning for scale, we can look at some other types of deployments that have been used for decades, even back in the days of racked computers and hardware switches that were real world. So let's talk about some of those. So actually, we can start with a rolling update, which is what we were just talking about. So the concept of a rolling update is just what we said, where over time, the release candidate replaces the current release. And eventually you arrive at a place where your whole infrastructure is running the new version. And it's already been tested and it's ready to go. This doesn't give you too much rollback capability, and there's not a lot of automation. So blue-green deployments are another option, sometimes called red-black. You can find blogs that will argue those are subtly different. You can also find blogs that say blue-green is a rolling deployment, but that's not really true. Blue-green really indicates one thing, which is you're running in an environment and you set up a second environment with your release candidate and test it, and you have a load balancer ready to shift traffic, and when everything is working, you shift over to the new version. And if anything goes wrong, you can shift back to the old version as a rollback. So that's a very common way to deploy software. And then there's also just sorts of interesting cases, like A/B tests are really common. So this allows you to set up two identical environments with different versions of the software, and then maybe looking at header content, you can say, well, this is for LTS customers, and over here we have our beta or our development customers, and they can use these new advanced features. So however you're going to do this, you're going to look at a strategy that probably already exists, and realize that with containers, a lot of this is a lot easier than it used to be. When you used to have to walk around with a laptop and a DB9 connector and go out into the data center and actually do these things by hand, well, using infrastructure as code, using Kubernetes, we can deploy changes on the fly that are really not expensive. It's easy to test a small, allocate new cloud resources and test a small thing. And you can automate a lot of this in code, which is really important. So as far as the strategies go, the wheel doesn't have to be reinvented, but we can look to modern technologies in the cloud to make these things easier. And a really good case in point is something that's become very common, which is a canary release. This wasn't super common a long time ago, but with these new sort of capabilities of being able to use virtualization and being able to configure your network traffic on the fly, it's a lot easier. And in a canary release, effectively what you're doing is an incremental deployment over time while you're monitoring the health of the application, and you can roll back at any point. So looking at that, basically you're looking at the health of the application, you're looking at the health, and these are metrics that you'll define, and you'll define your thresholds for failure. But you could say, well, let's look at HTTP responses for the user. If we hit any failures, we just immediately roll back. And now that canary is done, and we're back to production of the current release, rather. And we basically suffered a couple of failures that you saw coming, and you rolled back. And now you can go and triage those. You've got observability in place with logging and metrics. You'll be able to find what happened, debug that, kick off another canary release, and if everything goes according to plan, eventually your entire application is rolled over to the new version. So however you do this, it comes down to the same sort of semantic functions. You need to map your deployments to your commits, which is around using Git and understanding that, when you build a container from your repo, you know what version that is. You're going to manage your version deployments. You'll need to be able to configure granular, your traffic control needs to be granular. You need to be able to configure between different versions running. You're going to need to monitor the health of the system and the components while it's running. And you're going to have to keep the door open to invoke a rollback in case anything goes wrong. And you're going to automate all of this. And that leads you toward a lot of implementation of a DevOps methodology. So DevOps isn't a product, it isn't a software you buy, but it is a methodology for bringing ownership of the code closer and more into the wheelhouse of the developers that write it. And these are all aspects of things that need to be automated when you're practicing DevOps. The whole time we're talking about this, we have to remember that I'm advising you to own less code. And that sounds like a lot of automation. We want you to own the business logic that differentiates you and is your value proposition for your users. That includes your application's runtime configuration, the deployment specifications. But unless there's a very good reason to do so, you should really not own more than you need to, right? So lean on the systems and the platforms that you've chosen, like Kubernetes, and also manage services in the cloud for anything that you can. Because really, when you start automating this workflow, the logical goal is you arrive at what we're calling GitOps in the community. And surprise, this is a clandestine GitOps talk. You didn't see that coming. But no, honestly, this is nothing new, right? GitOps to me is just the next layer of abstraction and automation around these same concepts. So Git is the source of truth for your application and your infrastructure. Everything is version controlled, and you're using immutable deployments. You're leaning into declarative configuration using Kubernetes, infrastructure as code, Terraform, CloudFormation. And you're effectively extending the CI/CD patterns that we've been building on for years, resulting in fully automated, hands-off deployments, from the Git commit all the way through to running in prod. This gets you to a place where your developers are no longer spending their time babysitting their deployments, right, which is a good thing. So that leads us into one of the managed services that I think can play a crucial role that's AWS App Mesh. So App Mesh is a fully managed service mesh, and it provides a ton of solutions and automations and features around traffic management and granular in application-aware intelligent routing, but also in security and observability. It offers a lot. And so a lot of these things aren't new to service mesh, right? And that's a thing that, people say, well, I already use Prometheus or I already have load balancers. None of these solutions are unique to service mesh. It's how the service mesh implements the solutions that's really worth considering. But let's take a second, have a little reality check, right? We're talking about deployments in this talk. Why don't we just use load balancers? They're already in place. Weighted traffic groups are awesome. And that is true. For a lot of applications, you can just use weighted target groups on a load balancer. For example, we have a stack here that a blue-green deployment. So the blue stack's running, and we deploy green, we test it, we shift our traffic there, and we're ready to go. It's very simple. And it can work really well. But what happens if those stacks aren't, replicas of a monolith, but rather several microservices working together? What happens then is you end up either having every service make top calls through the load balancer, or every service needs their own load balancer, or a group of services that can share an endpoint would need their own load balancer. And again, this can actually work really well for you, but at scale, it starts looking pretty complex. And you end up paying for a lot of east-west load balancing traffic where maybe that's not ideal. And it's a lot to manage at scale, and you end up having to automate that very stuff that you're trying to make simpler. So that's where proxy sidecars come in. And Envoy is a project that's been around for a good long while. It's very mature. It is one of the first, I think it's the second CNCF project to graduate after Kubernetes. And this is a highly performant cloud native proxy that provides not only client-side load balancing, which is what we're after, with granular traffic control, but a ton of other features. From resilience features like retries and timeouts, rate limiting, outlier detection, through to security features around TLS termination. I mean, there's a lot of things that you can do with Envoy, and it has really nice APIs. They're very feature rich, and you can do a ton of stuff, which gets you right back to this complex situation of having to manage something that's really difficult to manage at scale. And with containers, it actually gets a lot worse, right? Because now every container instance is going to have a proxy. This is really complicated, and it would require quite a lot of automation and abstraction. And again, we should have a goal of owning less code. So this is the case for a service mesh. So basically, we have these requirements. We need service management, we need configuration, we need connectivity, we need client-side load balancing. We have a lot of services with a lot of instances of each service. So sometimes we're looking at thousands or tens of thousands of containers supporting hundreds of microservices. We have a lot of moving parts which are ephemeral in nature. And proxies are a really good solution here, but they can be complex to configure. And that's why we built Appmesh. So it facilitates the management of a very powerful data plane while offering a fully managed, really easy to use control plane. And I will say easy or simple. I mean that in relative terms. Appmesh does provide very easy to use constructs that they do the heavy lifting for you of building and managing a service mesh. So like we see EKS removes the undifferentiated heavy lifting of building clusters and managing their lifecycle. We see Appmesh as a way of removing that heavy lifting of managing your configuration for an Envoy data plane and a service mesh. And once you're using it, there's a lot of other solutions that are there at your fingertips, from beyond the traffic management, security and policy management and enforcement and observability solutions. There's a ton of stuff, which is the next part where people say, well, that sounds a little too good to be true. But if you understand how it's working under the covers, it makes a little more sense. So let's talk about that quickly. So effectively, you have two services. Say they're HTTP clients are going to talk to each other, or services rather. When we use Appmesh, we're going to create a data plane where each of these services has an Envoy proxy instance. And we will use Appmesh and its configuration constructs to inject the Envoy configuration for us. And so we're able then to have the situation where these two services exist. They are not aware that they are part of a service mesh, and we can do very robust, very granular control of the traffic, and we can also use resiliency features. We can do a lot of things here without any changes to the application code, which is really powerful. And so how we do that is by defining a few things. So we have a virtual service, which is a configuration abstract in the service of a service in your cluster. For example, a Kubernetes service by name. It's something you can find. We have defined a virtual router, which will define the traffic management for a given virtual service. And then we have virtual nodes, which will abstract and configure an Appmesh configuration endpoint for things in your cluster. For example, Kubernetes services and pods running in deployments. So that's sort of a lot to take on. So let's look at an example. So we have weighted traffic, which is what we're interested in. So we defined a virtual service named foo for the foo service, and we have two different versions here, blue and green. And we define virtual nodes representing both of those. So say we'll call one foo prod and the other one release candidate 1. And then we define a virtual router. Now, all of the stuff here in purple, the service, the router, the nodes, that all becomes configuration that Appmesh will then turn into Envoy configuration, and it will inject into the Envoy proxies that are running and handling the traffic for your pods. And so what this looks like under the covers is that the control plane in Kubernetes is actually running Envoy container proxy instances as sidecars in each of your pods where your microservices are running. So Appmesh manages the configuration fully through the control plane, and Envoy manages all of the traffic on the wire. And when we're using Kubernetes, we can use the AWS App Mesh controller for Kubernetes, which is an open source project that provides a set of custom resources, or CRDs, that map to the Appmesh API. And they will automatically inject those sidecars for you and make sure that they're running. And the controller will also monitor any changes in those CRD objects in the Kubernetes cluster and will reflect those changes up into Appmesh on your behalf, which then in turn gets turned into Envoy configuration, which is sent back down to the cluster. So pulling this all together, it becomes really seamless to use Appmesh in a Kubernetes cluster to define something like weighted targets. So here in this handful of lines of YAML, we're specifying an Appmesh configuration and we're applying it to the cluster. And with these lines, we're actually able to say, well, send 80% of my traffic to foo prod and the other 20% sent to the release candidate. So this is also, in my opinion, really simple, especially for the amount of problems you're solving. But let's be fair, there's more to learn. There are more moving parts, and you might have concerns about latency, cost, and complexity. But again, a reminder that you have to solve for these problems at scale anyhow. So I would argue that the complexity of learning a few CRDs and how to use the controller certainly is not greater than having to figure out each one of these individual problems. For example, routing traffic to multiple versions. And Appmesh is free to use. So there are processes that will run. Your proxies are going to run in your data plane, of course. You might induce a little cost there. You might induce a little latency. This is something you're going to have to look at and weigh in the balance of all things considered. But I will say again that I find this to be a relative simplicity. Developers will learn a handful of Appmesh constructs and their CRDs, and Appmesh just becomes a transparent feature of the cluster. And you can now specify aspects of runtime behavior and traffic on the wire as part of your Kubernetes deployments, which is great. And you're bringing along all of the other aspects of the features and solutions that Appmesh supports, like observability and resilience and security, and a lot more work is happening here in the near future. So looking specifically back at our deployments, if we're looking at traffic shifting, that was a pretty simple way to actually drive traffic to particular endpoints. And we can use that to specify rolling deployments or blue-green deployments, canaries. Really, there's a lot of different things that we can do here. You can be very creative. But of course, you're going to have to automate all of that. And that's where a couple of open source projects come in. So one is Flagger. This is maintained by the folks at Weaveworks. This is a progressive delivery operator that you can install alongside Appmesh controller in your Kubernetes cluster. And again, you have a little handful of CRDs where you can specify things like canary releases, blue-green deployments. This is very powerful. And so you're able to actually in code specify a deployment. And then in the cluster itself, you can use Flux, which is sort of the business end of a GitOps controller. So this is actually going to monitor your repos and pull in new YAML as you're making commits in your source repo. So your developers are working, pushing changes, and Flux will just kind of keep an eye on things and make sure that the state of the cluster is reflected. So really pulling all of this together, you have this automated stack of really great workflow that you're completely able to configure and control, and using a couple of pieces of open source software as well as managed services are able to arrive at. And speaking of managed services, since we're leaning into infrastructure as code and declarative configuration of Kubernetes, we have the AWS Controllers for Kubernetes project, which enables the configuration of use of managed services in AWS directly from Kubernetes. This is an open source project that's relatively new and currently supports a lot of services right now, from API Gateway, ECR, SNS, Elastic Cache. And you can see again, we're working with a CRD, and the controller will take care of using your credentials on your behalf to talk to AWS and configure services. So this is also very powerful. And sort of pulling all of this together, you end up with a very robust solid system where you can automate change and have some confidence in its resilience. And that, to me, is table stakes for building applications at scale right now. Teams are empowered to run fast at problems without having to worry about babysitting their deployments. And when you're able to fix issues as fast as you can and add new features and even refactor and redesign components at will, it gives you a lot of power in sort of solving your problems as fast as you can move. And there are other ways to implement this. I want to be fair, but in the spirit of sort of owning less code as a goal and leveraging the systems you've chosen and passing off undifferentiated heavy lifting to manage services in the cloud, this actually becomes a really compelling way to build your deployments. And once you've invited Appmesh to the party, you get a lot of other things invited as well into your ability to basically change Kubernetes YAML and then modify traffic flow or resilience features. So for example, adding a retry policy is as simple as this handful of YAML, and you can actually offload every retry loop you have in every microservice you have and standardize it and push it off into the infrastructure service. So this is a very powerful pattern. So if you're interested in this, or if you're new to Appmesh, you can take a look at the Appmesh examples repo, which has a ton of options of exploring small little demo applications to research all of these different, to explore and play with all these different features. And always, the AWS Container Services, and actually in AWS, all of our work is driven by our customers. So if you're interested, you could come by the Containers Roadmap or the Appmesh Roadmap, take a look at what we're doing, what we're working on, and if you have ideas or things that you want to see happen, please open an issue. Thanks so much. I really hope this was useful for you. And reach out anytime. I'm on Twitter, and always happy to talk about this and anything related. Thanks.